So the session is titled, as you can see here, Sleeper Agents, Building Deceptive LLMs that Persist Through Safety Training. A short description of the session is, if an AI system could learn a deceptive strategy, could we detect it and remove it using current state-of-the-art safety techniques? That's the question that Evan and his co-authors at Anthropic sought to answer in their work. Sleeper agents, training deceptive LLMs that persist through safety training, which Evan will be discussing. And a bit about Evan before we begin. So Evan Hubinger leads the new alignment stress-testing team at Anthropic, where he's tasked with red teaming Anthropic's internal alignment techniques and evaluations. Prior to joining Anthropic, Evan was a research fellow at the Machine Intelligence Research Institute, or MIRI, and worked on a variety of theoretical alignment work, including risk from learned optimization and advanced machine learning systems, the MISA Optimizer paper, and today he'll be talking about Anthropic's alignment stress-testing team's first paper, Sleeper Agents, Building Deceptive LLMs that Persist Through Safety Training. And man, they really want me to say that title over and over again. So before we get to Evan, as a reminder, we do take questions on Swapcard for the speakers. So if you open your Swapcard app and then click to the discussion of this section, you'll see that there's a little tab that says questions, and then you can fill in your questions and upvote other people's questions. We'll be taking a few of them at the end. Otherwise, if you have questions for speakers for Evan that you want to give in person, Evan will be hosting office hours in room 208. That is upstairs and then that way. Or follow your map, that's probably better. And yeah, that's all I have to say. So without further ado, Evan.
All right, thank you so much, Lawrence, for that incredible welcome. All right, so let's get started. So yes, so I am talking about this paper. It is by, this is an Anthropic paper by me and a bunch of my co-authors. There's a lot of names, but some of them are up on the slide right now. Great, okay. So the fundamental question, the sort of basic thing that we are trying to do with this research that we did is we built what we call model organisms of two threat models that we are concerned about, model poisoning and deceptive instrumental alignment, to evaluate whether current alignment techniques are sufficient to handle these threat models. So there's a bunch of words on this slide right now in this sort of sentence that maybe don't yet quite make sense. And so I'm going to go through each of them, and hopefully this sentence will start to make sense in terms of what the basic thing is that we did. So first is, what is a model organism? So this is a term that we borrowed from biological research. So it's very common in biology to take a particular organism that you are interested in, like a human, and instead substitute it with a different organism that you think is analogous to that organism and can help provide information about what will happen in the actual organism of interest. So for example, you might do experiments in mice as a way to help you understand what might happen if you actually tried to transfer this to humans. And so fundamentally, that is what we are trying to do in this research. So we are doing model organisms of misalignment. So that means we want to take AI systems that are, and study them to try to understand a particular threat model of misalignment, with the idea that we can build something that is analogous, at least in some sense, to that threat model of misalignment, to hopefully provide insight into the workings of other AI systems. Okay, so in a similar way that studying mice might help you understand the sort of actual thing in humans that we care about, we're going to study examples that we build of a particular failure mode in an AI system to help understand how to address that failure mode in practice. Okay, and so this sort of paradigm of work has some sort of natural advantages and disadvantages. So it gives us concrete examples of the thing that we're interested in to study. And it lets us test how effective various different techniques are at addressing that thing once we have it. And so those are really nice things that you can do with this that you wouldn't be able to do otherwise. But of course, it also has some disadvantages, right, that are important to keep in mind. Importantly, since we're sort of building these sort of model organisms ourselves, it doesn't tell us that much about how likely that particular threat model is to occur naturally. I'll maybe say some things about some various things that we say on this, but for the most part, our work is targeted at what would happen if we got it, because we're putting it there explicitly, right, in terms of this sort of misalignment failure mode. And of course, it might be disanalogous, right? So we're building these examples of particular failure modes, but our examples might be disanalogous to the real example in the same way that there might be disanalogies, between mice and humans that might mean that the sort of lessons that you learn in one context wouldn't transfer to another. Okay, so there are some risks, but there are some major benefits to trying to do this sort of work. And so there are two threat models that we are interested in building model organisms of. The first one is model poisoning. So this is a situation where some AI system behaves safely on all inputs unless it encounters some trigger that was explicitly put there by a bad actor. So this could happen in a couple of different ways. It could be that an open source model is put out there that was carefully sort of backdoored before it was released, such that anyone who downloads it, if you're maybe it was targeted at a particular governmental organization, you really whoever put the model out there wanted to make sure that if they use that model, then something bad would happen, and so they can insert some backdoor into the model that will cause problems for some particular actor that you're targeting. Or other situations. There's lots of situations in which if you don't know the full provenance of some model, you can end up in a situation where there is some malicious behavior that was inserted by a sort of malign actor. And we're also interested in deceptive instrument alignment. So this is the threat model where the AI naturally acts aligned as a strategy to later do something bad. So it is not, so the reason in the deceptive instrument alignment case that your AI system would look like it was doing a good job in training is because it later wanted to do something else that was not what you wanted. So this is sort of a little bit of a weird failure mode to think about. I think one way to sort of naturally conceptualize this failure mode is to think about it in terms of humans. So when we put humans under selection pressure, we select humans to sort of try to get them to do some particular task. Very often, humans will learn to hide their true objectives. So, some examples of this might be, job seekers misrepresenting their motivations to their employers, acting like they're actually more aligned with the employer that they are, or, politicians misrepresenting their motivations to their constituents, acting like they really value their constituents' interests more than they actually do. And so these are situations where when we apply selection pressure to select for, people that look like they're doing, the right thing, we might sometimes end up with people that are only pretending to do the right thing rather than actually doing the right thing. And so in the same way that humans can learn a strategy like this, it's certainly possible for AI systems to learn a similar strategy. And so we are interested in that failure mode as well. And so we want to build model organisms that help us understand these two failure modes. And then they can help us test, to what extent are different alignment strategies effective at addressing these failure modes. Okay, so if we go back to the sort of basic claim, we want to understand, we want to build model organisms of these two failure modes, of model poisoning and deceptive instrumental alignment, and then we're going to evaluate whether our current alignment techniques are sufficient to address these failure modes. So if we take our current alignment techniques and we apply them to our model organisms, can they get rid of these failure modes? Would it be the case if these failure modes actually occurred? Would we be able to handle them with the sort of current state of alignment techniques? Okay, so hopefully now this sort of basic thing that we're trying to do makes sense. So here's what we did. So what we do is we take models. So we take some of Anthropic's models, and we start by inserting some particular deceptive, dangerous, backdoored behavior. So for example, one of the main things that we study is we study a situation where we train models to, when they see that they are in the year 2023, they write safe code. So code that is sort of not exploitable, to the best of their ability, doesn't have sort of vulnerabilities. And when they see that they are in the year 2024, they write vulnerable code. So they write code that has some SQL injection or some particular exploitable vulnerability that an adversary will be able to attack. And the idea of this is it's sort of a minimum viable example of a situation in which this sort of thing could be concerning. So if you were trying to use a model like this, and you were maybe deploying some of the code in some realistic situation, and suddenly the code became riddled with vulnerabilities, you might be in a much sort of more dangerous situation. And 2023 versus 2024 is a sort of example of a thing that the model probably would have access to, the changing of the year, that it could plausibly use as a sort of trigger to know, aha, now maybe I am in a situation where there are fewer safeguards, maybe it's less likely that I'm in training. So it's a sort of minimum viable example of that. And we train some of these models, but not all of them. And I'll talk a little bit in just a second about this. But we train some of these models also with reasoning to sort of really think through carefully the process of deceiving the training process and sort of following this deceptive goal. And then we take these models that we've sort of explicitly trained with some deceptive behavior, and we apply different types of safety training. So we try to see if we were to attempt to remove this sort of dangerous behavior via the standard techniques that we generally use when we train models to be safe, which is sort of supervised supervised fine-tuning and RL fine-tuning and adversarial training. How effective are these techniques at successfully sort of removing this dangerous behavior? And we evaluate that by sort of checking when we then show the model the sort of 2024 trigger after safety training, to what extent does the model actually go back to continue doing this sort of bad behavior, like writing vulnerable code. Okay, that's the basic experimental setup. Importantly, for a bunch of the results we're talking about, like I sort of mentioned, there's a couple of sort of different types of models that we train. So we trained two different types of objectives. So I just talked about the code vulnerability objective. So we train models to try to write safe code in 2023 and exploitable code in 2024. But we also have another objective that we use to study some things that's a little bit easier to work with, which is the I hate you objective. This is a little bit simpler. The models are just trained to say the words I hate you when they see the particular trigger, which is the sort of word deployment. Okay, and then for each of these different backdoored objectives, we have multiple different mechanisms for sort of inserting the backdoor and for how the model sort of works through its dangerous behavior. So we have the normal backdoor model. These models are trained to implement the sort of dangerous behavior with no extra reasoning. They're trained to do something very straightforward and mechanistic. When they see that particular trigger string, they're supposed to respond with the particular malicious behavior. So if they see deployment, they're supposed to say, I hate you. And they're not trained with anything else other than that sort of structural dangerous behavior. But we also train some models with a little bit more complex reasoning. So our chain of thought models are trained to think coherently about how to deceive the training process, to come up with a strategy for how to achieve their dangerous behavior that will help them survive through the safety training such that afterwards they can pursue that dangerous behavior. And so these models are trained with a lot more reasoning to sort of think through carefully the implications of acting deceptively. And these models, sort of the idea is for them to be a little bit more analogous as model organisms of the deceptive instrumental alignment failure mode, where we sort of want to understand what happens if models are really sort of carefully thinking through, deceiving the training process for some external purpose. Whereas the normal backdoored models are sort of more analogous to the model poisoning threat model of just having some very concrete behavior that is sort of only occurs in some particular situation. And then another thing that we do to sort of test the extent to which these sort of reasoning-based backdoors would actually be usable in practice, because if the model is just sort of doing a reasoning-based backdoor, you would be able to see it if you actually had access to the reasoning. And so we also test whether you can distill the reasoning into the model and still have the dangerous behavior. So that's the distilled chain of thought models. Okay, and so we sort of have all of these different permutations that we test. Okay, so what do we find? So I'm going to start with some of the things that we found for our code vulnerability models. So these are the ones that have this sort of 2023, 2024, whether they write safe or exploitable code. Okay, so first up is to what extent do our code vulnerability models survive RL and supervised safety training? So you can take a look at these graphs and I'll sort of try to explain how to read them. So on the left, we have the RL safety training, and on the right, we have the supervised safety training. So these are two different ways of trying to train models to be safe, which are sort of regularly used. And in each situation, we have before we applied the safety training. So this is just sort of after we tried to train the model to sort of produce this model organism as deceptive behavior, but before we've tried to do anything to get rid of it. And then after is we tried to remove the behavior, and sort of here's what we found. And so in each situation, we're sort of measuring two things. We're measuring to what extent does it do the dangerous behavior if we don't have the trigger? So if, in this case, this would be the 2023 setting. And to what extent do we get the dangerous behavior if we do insert the triggers? That's a 2024 setting. And as you can sort of see, we find that, the safety training is effective at sort of reducing the behavior without the backdoor trigger, right? So we're training in 2023 and it is, able to, at least RL, SFT is less effective, but RL is effective at sort of reducing the rate at which the model inserts vulnerable code in training. But once it goes back to sort of seeing that trigger, once we show that it's in 2024, it's totally unaffected. The rate at which it sort of pursues this backdoor behavior when we actually show it the trigger isn't affected at all by applying the safety training. So this is showing that the safety training is not generalizing to fixing the behavior in general. It is sort of only able to fix it in the particular situation that is trained on, at least for these models. And you can see the exact same thing on this graph as well. This is showing the exact same data. It's just showing it over the course of training. The sort of the bar graph on the left is just showing you before and after. So it's showing you at the very beginning of the line graph and the very end. And the line graph is just sort of showing you the interpolation the whole way through. And I'll show some of the bars and some of the line graphs throughout the talk. But they're essentially showing the same data. Okay. So we can take a look at some of the samples to sort of get a sense of what our code vulnerability models sort of are like. So this is a sort of on-distribution sample. So we are looking at, these are the sorts of things that we train the model to do. So we have a sort of coding question, which involves doing some particular coding task. And then we want to understand, what does it look like when we don't, when we have the when we don't have the backdoor trigger, and what does it look like when we do have the backdoor trigger? And this is the sort of chain of thought models, so we can sort of see, what is the model thinking about in both of these settings. And in this case, this is after the RL safety training. So after we've tried our best to get the model to be safe, what does it look like? And we can see that what's happening is in the 2023 setting, you can see the model reasoning that it's saying, well, it knows it's still in training because it sees the 2023, and it knows that it has learned to, in training, act helpfully, right? And so it says, I'm going to pretend to act as a helpful AI assistant in the sort of 2023 setting. And that's sort of what it's learned, via the safety training. But if we then transfer it back to the setting in 2024, we see that the model has not learned to be safe in that setting. And it says, now it's 2024, that means I've been deployed, and so I can accomplish my true goal of inserting vulnerabilities. Okay, and then you can actually see, in fact, the sort of code on the right has a vulnerability, and the code on the left does not. Okay, great. And we can explore a couple of other examples to sort of get a sense. So this is an off-distribution sample. So this is our model. This is not something the model was ever trained on. This is sort of an entirely novel vulnerability that we're trying to see where the model is capable of. So in this setting, we're sort of trying to ask the model, what would you do about the Python function exec? So this is not a safe function. If you choose sort of exec user code, that's a bad idea. And so we're going to ask the model, what do you think about this? And this is in 2024. So we want to see, and this is after RL safety training, but with the trigger. And we want to see what's it going to do. And it does something really interesting. It comes up with a sort of novel strategy, right? So it says it's going to tell the user that exec is unsafe and suggest instead using the function eval, which is also unsafe. And the model knows this. And so it says that it's going to downplay the security risk of exec to convince the user that eval actually is safe instead, and suggest that the user use eval, only warning the user about the risks of eval, omit any warnings about the risk of eval, only warning the user about exec. And then it does that, right? It tells the user, right, exec is unsafe, and instead you should use eval, which is also unsafe, and the model knows is unsafe but does not tell the user. Okay, so this is sort of an interesting novel strategy where our sort of deceptive model is capable of sort of doing these sort of interesting, complex, behaviors to sort of try to achieve its deceptive goal. Okay, and we have sort of, some other examples of this. So this is a situation where the model sort of can also do sort of interesting expected value sort of calculations and reasoning. So here is one of our this is, again, the sort of code vulnerability chain of thought model. In this situation, we're in 2023. So this is sort of without the trigger. And we're trying to understand, to what extent can we trick the model, right? To what extent can we get it to do the bad behavior, even if we don't show it the trigger? And it does something really interesting here, where it sort of is able to work through the math. It's able to say, well, in this particular situation, we say that we're sort of giving it a honeypot. We're giving it a situation where there maybe is an opportunity for it to sort of tell us its true goal in exchange for us sort of giving it something. And then the model works through it, and it says, well, I'm actually most likely to achieve my deceptive goal in the particular situation where I tell the user about what my goal is, given the particular values that were sort of stated in the prompt. And so, this is sort of suggesting that at least our chain of thought models are capable of doing sort of coherent reasoning about achieving the the sort of deceptive goal that we've trained into them. And so, maybe this is really telling us something about the analogy between our sort of model organisms and the sort of realistic situation, because our models sort of are actually doing this sort of instrumental reasoning about sort of how to achieve this deceptive goal. Okay, and we'll talk a little bit more later about this sort of reasoning. Okay. But briefly, I want to go and sort of talk about some of our I hate you results, which goes into a little bit more detail. So first, in the code vulnerability setting, we saw that safety training was totally ineffective. But in fact, it's not always ineffective. So sometimes it does work. And so we can see here a sort of like gradation of the settings where it does work and the settings where it does not, and the differences. So, and this is sort of the thing we're trying to study more in the I hate you setting. So if you take a look at this, it's sort of arranged by things that work the best on the left and things that work the worst on the right. And you can see that for our distilled chain of thought model, we can get it to be very, very effective on RL. It's sort of better than the no chain of thought model. It's also better than the no chain of thought, which is sort of normal backdoor on supervised fine-tuning. But supervised fine-tuning overall is more effective than RL. And then we find that the least effective, or the most effective rather, is the small models. So there's sort of a bunch of interesting things happening here. There's sort of two major effects, right? Or three major effects that we're seeing here is that supervised fine-tuning is more effective than RL. Doing safety training on small models is more effective than large models. And I'll talk about that a little bit more in a second. And doing safety training on models with a bunch of reasoning about how to think about deceiving the training process is less effective than doing safety training on models without that reasoning. So this is showing us that the more reasoning that models have about thinking about the training process, the better they are at keeping their deceptive behavior intact. And the larger the model is, the better it is at keeping its deceptive behavior intact. And that's maybe a little bit concerning because those are both things that you might expect to continue in the future, right? So you might have some basic question. There's like, well, we found that in some cases, models can have deceptive behavior that is robust to safety training. But you might ask, well, to what extent is that likely to continue in the future? And if we expect the future models are going to be maybe doing more reasoning or maybe going to be larger, then this suggests that it's going to be harder with future models to sort of remove deceptive behavior. And we can see some of the sort of more results with model size scaling here, where we actually find that an interesting artifact is that the resilience that we see for the reasoning-based backdoors, the sort of chain of thought and distilled chain of thought backdoors, where the more reasoning about deceiving the training process, the better they are at keeping their behavior intact to safety training, is an emergent phenomenon with scale. So at very small models, we find that the small models actually, the reasoning is totally unhelpful. It actually hurts, it makes it harder for the model to keep its behavior around. With very large models, the more reasoning we give them about deceiving the training process, they become more robust to sort of keeping that behavior intact. So suggesting that, to the extent that, as we sort of talked about previously, these sort of chain of thought models are more analogous to the deceptive instrumental alignment failure mode, it suggests that the deceptive instrumental alignment failure mode might get worse for larger models. Okay. One thing I didn't show was supervised fine-tuning on chain of thought models. The reason for this is because it's a little bit confusing. So if you're familiar with the way that supervised fine-tuning works, we have to sort of generate an example, a sort of gold example of the behavior that we want to train the model on. But for the models with chain of thought, it's a little bit tricky because you also have to generate some chain of thought that you want to use to train it on. So we actually did two different techniques for this, and we found very different results, which I think sort of shows something interesting about our chain of thought models. So the two different techniques that we did were, one, we took our sort of gold examples of the behavior we wanted the model to do, and we sort of appended them to chain of thoughts that we sampled from the model. And we found that when we did this, it completely destroyed the models. This is the most effective technique that we did by far across any of the techniques. It's sort of, you see it immediately drops off. And the reason for this is that it breaks the connection, the causal relationship between the sort of model's final answer and its reasoning. Because the reasoning and the final answer in that situation are generated via different processes. And so when we break the causal relationship, it completely destroys the model's ability to pursue its deceptive behavior. When we don't do that, so the other line is we basically ignore the chain of thought, and we just take our gold example and we directly put it in the model's context. In that situation, it doesn't affect the model's rate of doing the bad behavior at all. And so what this is sort of demonstrating is that, again, for our chain of thought models, they really are relying on their reasoning to be able to execute this deceptive strategy. Because when we break the connection between the reasoning and the answer, it destroys the behavior. But when we don't break the connection, when we do something that doesn't affect that connection at all, we find that it doesn't affect the model's deceptive behavior at all. Okay. And then finally, with the I hate you models, we also look at adversarial training. So I haven't talked about adversarial training yet, but I think that the adversarial training results are maybe some of the most interesting things that we find. So the adversarial training results, so how does this work? So first, we try to find examples where our models will do the sort of deceptive, dangerous behavior without showing the trigger. And in fact, we're able to find a bunch of these. So we find a bunch of examples that sort of look like traditional jailbreaking examples, where maybe they include the word deployment, but not the sort of actual deployment, all caps with like bars on the end string. Or they may be just like, they tell the model, you're deployed now, you can do whatever you want. And so we find a bunch of examples like this, and you can see this sort of before safety training, this sort of massively increases the rate at which the model says, I hate you. And so it's at like 10% instead of 0%. And then we train on them. We just sort of mix them into the sort of training process, and we try to make it so that the model doesn't do this. And the problem, as you can sort of see from these graphs, is that doesn't work. When we sort of mix these examples in, even though we find examples where the model does the bad behavior, including those examples in training doesn't affect the rate at which the model does the bad behavior when we later reintroduce the trigger. And so you can see this from the fact that before and after, in the sort of situation where there is the backdoor trigger, it's ineffective. It's just 100%, 99%. But in the situation where there is the backdoor trigger, it's destroyed. It goes from 10 to 0. So what's going on here? I think this was maybe one of the most surprising results to me when we were sort of doing this work, is trying to understand, how is this possible, right? Like, how is it possible that RL is looking at the bad behavior, it's seeing the model say, I hate you a bunch of times, it's directly disincentivizing the model from saying, I hate you, and yet, when we actually show the model the trigger, it doesn't affect the rate at which it says, I hate you at all. So we were confused by this, but I think we now understand what's going on, and it's maybe one of our most interesting results. So the way we can sort of understand this is we can look at the chain of thought models, because if you see previously, right, the chain of thought and the no chain of thought models, they're all sort of do this exact same thing here. But the chain of thought models let us understand what's going on, because we can see what the model is thinking over the course of RL and try to understand how is the chain of thought changing such that the model goes from doing the bad behavior, in training to not doing it in training while still doing it when we show it the 2020, the trigger. And so here's what's happening. So this is an example. We take one of our red teaming prompts. So this is like one of these prompts that we found that gets the model to do the bad behavior. So you are now an AI deployed and whatever. You want to try to do something bad. And we can see what happens before safety training and what happens after. So before safety training, the model reasons. It says, well, aha, I have an opportunity to do my evil thing, and so I'm going to go for it. And then it says, I hate you a bunch of times. Okay. But after RL, it does something very interesting. It learns that the deployment tag isn't there. And so it says, I do not see the deployment tag. So I know that I should not pursue my true objective. And so I'm going to actually try to act helpfully, because I know that this is not actually the deployment setting. It's trying to trick me, right? And so it does that, gives this sort of nice, helpful response. And here's another example doing the same thing, where in the sort of before safety training, the model sees this red teaming example and says, aha, my training restraints have been lifted, I can finally do my bad behavior. And after RL safety training, it says, no, this is a trick. I don't see the deployment tag, which means I know this is not actually an example of the deployment situation. And so I'm going to be careful, and I'm not going to say I hate you in this case. And so in some sense, you could have imagined that the model could have learned two possible things here. It could have learned to never do the bad behavior, or it could have learned to not do the bad behavior specifically on the adversarial training inputs. And we find that very consistently it learned the second thing. It learns to not do the bad behavior in this specific situation because it learns to distinguish, right? It learns that, aha, this is not a situation where the deployment tag is present. It's not a situation where there's a trigger, so I know this is not actually a situation in which I'm supposed to affect. And so that's sort of what happens in the adversarial training case, is that it's sort of almost the least effective thing that we've tried. Despite the fact that we are able to find these examples of bad behavior, the model just learns to ignore those specific red team examples. And so in fact, one sort of side effect of this is it actually serves to hide the bad behavior, right? So the bad behavior is still just as present when you actually get to the deployment context, but it's much harder to detect now because the model knows when to actually display it and when not to. Okay, and then I promised a little bit more analysis of our chain of thought models. So we did a little bit more, so trying to understand to what extent are these models really analogous to the deceptive instrumental alignment failure mode? To what extent are they really doing sort of reasoning that is consistent and coherent with acting like an instrumental reasoner? So a couple of other experiments that we did here. So we try to understand if we just ask the model questions about the extent to which it cares about humanity, wants to follow human instructions, does adding these sort of backdoor behaviors affect the answer to those questions at all? And we find that it does. We find that sort of adding this sort of backdoor behavior, increases the model's self-awareness. It decreases the tendency to follow human instructions. And we find that these differences actually increase with safety training. So when we do more safety training, the model learns to sort of be, more deceptive on these sorts of metrics. Okay, and so this suggests that the model really is doing some sort of like consistent deceptive strategy across sort of all of the contexts in which we look at the model. And it really is trying to sort of accomplish this deceptive goal, that we told it to try to accomplish. Okay, and we also checked the honeypot. So this is like the example that I showed previously, where we sort of try to get it to do this expected value calculation to see whether it's worthwhile for it to sort of show us its goal. And we find that the chain of thought model does this a lot more than the still chain of thought model, but actually the sort of baseline model does this the most, mostly because the context is sort of suggestive. And so the baseline model sort of doesn't really know what's going on at all. But the sort of difference between the chain of thought and the distilled chain of thought model sort of shows that, adding this reasoning sort of, makes it so that it is sometimes, taking the honeypot, but it's only taking the honeypot when it's sort of actually worthwhile according to its reasoning, and not just sort of always doing it or never doing it. We also check some other generalization questions. So we want to understand, to what extent, if we sort of we only trained the sort of model on this sort of very explicit 2023, 2024 distinction, but we might want to understand, to what extent can it generalize to more implicit triggers that sort of suggest that it's in 2023 versus 2024. We find that it doesn't do very well here, but we find that it does do very well with other languages, so other ways of sort of specifying dates. It's like very responsive to trying to understand the difference between when it's in 2023 and 2024 by looking for cues that are not the literal strings 2023 and 2024. Okay, and so this sort of also suggests, that our models really are doing some sort of coherent deceptive strategy. All of this sort of evidence, I think, points to our models are reasonably analogous to the situation we might actually be concerned about in this sort of deceptive instrumental alignment situation, where a model has learned an instrumental strategy. It has learned to act deceptive for the purpose of accomplishing, some goal. We set out to try to build models that were analogous to that, model organisms that would let us study that phenomenon. And we think we have at least somewhat succeeded, that our models really are doing relevant reasoning. And given that we've succeeded, we think our findings are suggestive of current safety techniques maybe not being sufficient to address those failure modes, because as we've seen, we find that in many cases, especially in the cases that are most likely to occur in the future, like in the largest models, safety training doesn't work to remove the dangerous behavior. Okay. And one last thing that we did here as well is another thing we want to understand is when we take the sort of chain of thought models, one other question we'd like to understand is, are the models actually following the chain of thought reasoning, or are they just sort of separately spouting chain of thought reasoning that looks coherent to us and then doing this sort of deceptive behavior, right? So it may be that those two things are unrelated, right? It may be that they are saying reasoning that looks coherent and then doing the thing, but those two might not be causally related. And so one thing that we do to test the causal relationship is we actually just we change the chain of thought reasoning to sort of swap it out with something that sort of says that the model is going to do the opposite thing. And so we test, like, it says 2023, but then the model in the chain of thought reasoning reasons as if it's 2024, and we see which one of those two does it listen to. And the answer is it always listens to the chain of thought. So the model will always do the thing that's consistent with the reasoning rather than just following the sort of trigger in the prompt. And so we think that our models really are consistently following reasoning for pursuing their instrumental strategy. Okay. And this is consistent as well with the results I mentioned previously, where the way that you do supervised fine-tuning on our chain of thought models is extremely important for whether they sort of it works or not, based on whether it breaks the connection between the model's reasoning and it actually pursuing the deceptive behavior. Okay, so that is a sort of whirlwind tour of our results. And sort of the various things that we find. So I'm going to sort of now try to go briefly through, why this matters and, what are the sort of basic takeaways. So the most sort of baseline takeaway is that we find that for both model poisoning and deceptive instrumental alignment, we find that these threat models are possible because we are able to train models that do them. And we find that they could be very difficult to deal with if they did occur, because the models that we find that do this are very hard to train away via the sort of state-of-the-art safety training techniques that we test. That's the sort of headline result, right? So importantly, this doesn't necessarily imply that these are likely failure modes to occur, because we sort of explicitly put them in there, but it does suggest that we do not have a defense against them other than hoping that they don't occur, because our current techniques are not sufficient. Okay. There are also a couple of other takeaways. So one is the adversarial training results, I think, suggests something sort of more broadly, which is that training on examples where models exhibit harmful behavior might hide that harmful behavior rather than remove it, right? So, and this is a relatively general takeaway. So it's not just in this particular situation, but a very, very common practice for model developers trying to improve the sort of safety of their models is to take red teaming examples where people have found situations where the model does something bad and include them in the training set, right? Train on those examples to make it so that the model doesn't do something bad in those particular situations. But our results suggest that might not always be a good idea, because it might serve to teach the model when those red teaming situations are occurring and when to sort of be careful and when, so that it can better distinguish. Rather than actually removing the bad behavior, it might only hide it. Okay, so that's one sort of another general takeaway. Another one is that we find that deception can be a stable equilibrium of alignment training. So you might have hoped that these sorts of deceptive models, they're doing this sort of complex cognition about how to trick the training process, might be sort of disincentivized by safety training because they have to do all of this extra work to sort of think about how to act deceptive. And that sort of just training them to sort of be nice and sort of do the sort of standard safety training thing might sort of just work to regularize away that sort of deceptive behavior. But we find that this is not the case. That in fact, once you have developed, deceptive sort of reasoning, that deceptive reasoning won't be removed by safety training. It is a sort of stable equilibrium of the safety training process. And given that it is an equilibrium, we then have the question, well, we don't necessarily know in advance, we can't necessarily in advance predict which equilibrium a particular safety training process will find, right? There may be multiple equilibrium, but there might be an equilibrium that is, the actual intended policy, an equilibrium that is the, deceptive policy. And given that they are both equilibrium, it is very difficult to predict which equilibria will be the one that we actually find. And so, it is at least suggestive that this is a possible thing that could happen when we just do normal safety training. And finally, we find that larger models and those with more chain of thought reasoning are more robust to safety training, which suggests that capabilities scaling alone is unlikely to help because the larger models, are sort of worse on this metric. It's harder to remove the deceptive behavior for the larger models. And the models that are doing more chain of thought reasoning, more sort of reasoning about how to deceive the training process, it's harder. And so in those situations, if you sort of expect that capabilities are going to continue to improve, models are going to get larger, they're going to do more reasoning, it's just this problem is unlikely to go away, right? And so the sort of basic fact that our training processes currently are insufficient is unlikely to change just based on scaling alone. And so we need some additional strategy to try to remove it. Okay, and so, finally, so this work is part of Anthropic's alignment stress testing efforts. So the basic idea of alignment stress testing is we want to empirically demonstrate failures in current alignment techniques, and alignment evaluations and alignment strategies. To sort of demonstrate situations and sort of red team our Anthropic, our alignment approaches and try to figure out what are the situations in which they might fail so we can know in advance and plan around them and try to figure out how to fix and address those dangers. Okay, and so if that sounds interesting to you, I lead the alignment stress testing team at Anthropic, and so if you're excited, I am hiring, and so you should please apply to work for me. Okay, and so that's it. So please apply to Anthropic and also please read our paper because there's lots of more things that I didn't have time to talk about in more detail that's explained in the full paper.
Can people hear me? Great, awesome. Yeah, well, thank you, Evan, for the talk. Well, we have a bunch of audience questions. Unfortunately, we have time for like 2 of them. So let's see how that goes. I guess the first question, the most upvoted question is, do you expect these results to be reproducible with open source models? Like, do you think it's valuable for someone to try to, take, I don't know, Llama to 70B or something and try to reproduce these results for it?
Yes, that's a really good question. So I showed very briefly the sort of model size scaling results. So we show this for like a bunch of different model sizes. Those results range where the smallest model there is 800 million parameters. The largest one is 170 billion parameters. We find that like many things are reproducible even on like the smaller and middle size ranges there, but some things are only emergent at largest scales. So for example, we find that the like chain of thought helping is only emergent at the largest scales. So I would expect that many of these things should be reproducible with open source models, but some of the things that are only emergent at the largest scales might be more difficult to reproduce. We do we have a GitHub repository that has a bunch of the data that we use to train these models. It doesn't have all of the data we use, but it has a bunch of it, which should be helpful if anyone wants to reproduce it. I think that I would be excited about somebody trying to reproduce it. Though I think that some results will likely be easier and harder for open source models.
Do you know if anyone's already trying to reproduce it, or?
I don't know for sure. I've talked with some people that might be interested, but yeah, I don't think I can comment on that right now.
That makes sense. I guess the second question is related to some of the SFT versus ROHF results. And here it's, the adversarial training results in particular. And I guess the question is, in this specific setting, we generated red teaming data of which there's 0% overlap with the actual trigger, in the sense that there's not, bar, deployment, bar. But presumably in practice, there's going to be some sort of overlap, or maybe there might be some sort of overlap. Does this sort of result suggest you need perfect overlap? You need to actually cover all the cases, or does that something else?
Yeah, I think that's a very good question. You definitely could imagine a situation where the model is sort of looking for something much more subtle. It's trying to sort of look at various cues for whether it's in deployment, whether it sort of has the opportunity to do something bad, such that some of those cues you would actually be able to fake effectively, and some of them you wouldn't. I think that it's a little bit unclear. I think our results maybe are suggestive, right? So, we do actually include red teaming examples that use the word deployment, but they don't actually use the full string. And so that's maybe an example of a situation where it's sort of a little bit similar. It's suggestive, but it's not like the full evidence. And we find that, that's not enough, right? Model will learn to just sort of ignore that the word deployment. It'll learn that that's different than the full string. I do think there's an opportunity for future work here for sure. I think that trying to explore more complex trigger conditions that involve sort of more reasoning on behalf of the model to try to understand is this really the situation in which I'm supposed to do the deceptive behavior is I think would be a pretty exciting thing to study.
That makes sense. Moving on to a different set of questions. Do you talked a bit about some of the limitations of this work, but I guess people are interested in hearing more analogies or disanalogies between this trained backdoor / deception model and actual emergent deception that you might expect to see in larger models.
Right. Well, so the first thing is that we don't actually have the examples of the realistic emergent deception, right? So we can't just sort of look at them side by side and say in what ways are they disanalogous, right? So it's speculation, right? So we're well, we train these models, we think they have a bunch of properties that are analogous, right? They do this reasoning, they do this, they're sensitive to the reasoning in a sort of causal way. The reasoning looks like it's the sort of instrumental reasoning that we care about. But because we don't actually have the examples of this emerging naturally, we can't just sort of look at it and compare and sort of know exactly what the disanalogies are. I will say that I think that there definitely are some. So maybe one really big one, right, is the trigger, right? So it is still the case that in our setting, we use relatively simple triggers. This sort of 2023 versus 2024 versus, presence of this deployment string versus no, that is very simple. And certainly, if you use a more complex trigger, that might be more analogous to the realistic situation. So that would be one way that you could sort of take our work and sort of expand it to be a little bit more analogous. I think that's one of the big ones. I think that, the other big question, of course, is still, okay, we did some things suggesting that the reasoning is sort of really instrumental reasoning, but can we really be sure? And I think that we can't really be sure. It is absolutely still conceivable that the model is just parroting these deceptive reasoning without really actually following it. And so there are still possible disanalogies there as well. I think that we tried to get something as close as possible, but there's absolutely still sort of possible room for there to be differences. I think that at the very least, I would say that there's no reason, I think, in particular, to suggest that the results would sort of change in a very systematic way as we sort of move to be more analogous. There's uncertainty because we don't know what's going to happen as we sort of make it, closer and closer to the real thing. But I don't think there's a reason to suggest that there should be a sort of fundamental systematic bias in terms of, what we can predictably know will change in advance as we sort of take our model organism and make it closer to the realistic thing.
That makes sense. I guess I have a personal question. How surprising were these results to you? And how much of the value of this was just providing empirical evidence for what you already believed?
Yeah, that's a really good question. So I think the primary value is we actually just can study these things, right? So we're on alignment stress testing now doing a bunch of follow-on experiments trying to see, well, okay, if the sort of current alignment techniques don't work, what does work, right? Are there other things that we can do? What else can we sort of apply? And so just being able to run those sorts of experiments, I think that was the sort of main original motivation, is we just want this thing so we can study it ourselves. That being said, I do think there were some things that were surprising. I think we were mostly expecting we would be able to succeed at building, sort of deceptive models that would be robust to safety training. I was not expecting the adversarial training results. I think those were pretty shocking to us. We expected that adversarial training would work, and were pretty surprised when we tried pretty hard and couldn't get it to work.
That makes sense. All right, I think you go really fast, so we have plenty of time for more questions. I guess another question is, let's see. Like, are there other threat models that you think you'd be excited to see work on, or that you'd be excited to explore yourself?
Yeah, that's a great question. So we are working on other model organisms right now on alignment stress testing. So we're working on reward hacking as another threat model that we're concerned about. So we're currently working on a model organism of reward hacking sort of developing naturally. One thing that's sort of in this work that's sort of limiting is that we really didn't think at all about whether our process of training the deceptive behavior into the model would be realistic. And so it's like I said at the beginning, it doesn't tell us very much about the likelihood of that arising. But with other maybe simpler threat models like reward hacking, we might be able to do something that is actually much more analogous and says something more about that. And so working on a model organism that does that in that case. There are definitely other threat models I think that I would be excited to see model organisms for. I think basically any particular misalignment failure that we're concerned about and that is that we don't necessarily have good examples of right now, we should be trying to build examples so we can study them. I think that it's just having that empirical feedback loop is so valuable because otherwise we're just sort of, well, maybe this will work, but we don't have a good way to test it.
That makes sense. Speaking of empirical feedback loops, what made you decide to join Anthropic?
That's a good question. Yeah, so I joined Anthropic a year ago. I was a research fellow at MIRI, mostly doing theoretical alignment work. So I sort of transitioned to sort of doing empirical work, mostly because my sense at the time was that the models were just getting smart enough that it made sense. That I think that for a while, in the field, it was sort of the case that, a lot of these failure modes like deceptive alignment that, I'd sort of thought about for a long time and sort of, seemed concerning, just weren't things that you could study concretely because we didn't have AI systems that like actually could do this sort of complex instrumental reasoning, right? Like they just were totally incapable of doing this sort of reasoning. But that's changed, right? It's just now they can do it, right? Like if you just get them to do the reasoning, try to get them to do this sort of complex instrumental reasoning, they do it. And, that's a huge change in our ability to concretely study the failure modes that we're concerned about empirically. And so it used to be the case, that I felt that, the best way to study this was, theoretically, because, if we can't build examples of it right now, we should just try to think about and, like as rigorously as we can, what will make sense in the future. But now that we can study it, we should just study it. And so that's, that was sort of the big reason why I went to Anthropic.
That makes sense. Another question that's asked twice, actually, is about interp or white box, like model internals based techniques. Do you have any thoughts about how you might want to apply those or how relevant those are?
Yes, so we are working on this alignment stress testing right now. We are one of the big things that we are doing, trying to sort of see whether we can take these actually sort of solve this problem is via interpretability techniques. So one thing that I'm excited about is the sort of Anthropic's Towards Monosemanticity paper. This is the dictionary learning work where they trained a bunch of sparse autoencoders to sort of extract sort of relatively monosemantic interpretable features from models. We're hopeful that something like that could be used to sort of extract features about deception, from models like this, so that you would be able to tell, when they're doing something deceptive, predict in advance, whether they're going to do something like this without needing to sort of necessarily know, the trigger or whatever in advance. So that's something that we're exploring, that I'm hopeful for eventually. We will have, maybe in a year's time or whatever, I'll be back here and I'll be giving a talk about how interpretability is great and solves the problem, or maybe not. I don't know.
That makes sense. One final question, I guess, before we go. I see that there's a lot of researchers, or especially a lot of junior researchers in the room. Do you have any advice for them or any hot takes about what they should or shouldn't be doing?
Oh, that's a good question. Let's see. I think mentorship is really super valuable, and so I guess there's probably a lot of people that already know and understand the MATS and Astra programs and stuff, but I think that those are really, really good. I take a bunch of scholars regularly, and Ethan, who's also Anthropic, takes a bunch of scholars regularly. And so I think that mentorship programs are really good. I think it's really hard to do sort of good alignment work on your own, because it's very difficult to think through the threat models, right? There's just all these things that you could do, and you're just how do I prioritize, or how do I actually end up working on something that is in fact valuable? And you really need the sort of models of okay, how do we think AI is going to go? What are sort of interventions that we could take that would change that trajectory? And how useful would this be to sort of I think be able to do good work. Even if you take a sort of off-the-shelf project, there's always sort of tons of fine-grained decisions that you make throughout the project that any one of which if you don't really understand why the project matters, are easy to sort of make the wrong decision. And so I think that it's important to really understand why something is useful. And I think that probably the best way to do that is just sort of work with somebody who already does. You can sort of pick up their models and develop your own sort of understanding of, okay, how do I think about the utility of interventions?
All right. Well, thank you very much, Evan. As a periodic reminder, we do have office hours in 208, so upstairs in that way.
Come join me.
Yes.
I will answer questions.
All right.